In this video, we're going to look at a test known as the alternating series test. Let's consider a series whose terms alternate in sign. So the first term is a positive, the second term is a negative, plus, minus, plus, minus, plus, minus, and so on. Or we could start with a minus, minus, plus, minus, plus, minus, plus, minus, plus, and so on. So here's an example of an alternating series. Here we have 1 minus 1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6. We can write this in a more compact way. Summation n equals 1 to infinity minus 1 to the n plus 1 times 1 over n. Notice what causes this alternating series to alternate is this part here, negative 1 raised to a power, negative 1 to the power of n plus 1, because negative 1 raised to an even power is plus 1. Negative 1 raised to an odd power is negative 1. And that's what makes it alternate. Let's look at another example. Negative 1 plus 1/4 minus 1 over 9 plus 1 over 16 minus 1 over 25 plus 1 over 36. So we have to get a general pattern for this. Well, the alternating part will either be negative 1 to the power of n or negative 1 to the power of n plus 1. But because we're starting at a negative, we should use negative 1 to the power of n. If you plug n equals 1, we get negative 1 to the power of 1. Negative 1 raised to an odd power is equal to minus 1. n is equal to 1 to infinity. Now notice the denominator. When we have 4, this is the same as 2 squared. 9 is the same as 3 squared. 16 is the same as 4 squared. So in the denominator, we should have 1 divided by n squared. Notice the nth term of an alternating series has the pattern an is equal to minus 1 to the n plus 1 times bn, or an is equal to minus 1 to the n times bn. And the factor negative 1 to the n or negative 1 to the n plus 1 is what makes it an alternating series, where bn is positive, and if you take the absolute value of an, we get absolute value of negative 1 to the n times bn, and the absolute value makes it positive, and we just get bn. All right, so the basic idea is if the terms of an alternating series decrease in magnitude towards 0, then the series converges and has a finite sum. And we say summation n equals 1 to infinity, negative 1 to the n times an converges. So let's look at the formal definition of the alternating series test. The alternating series summation n equals 1 to infinity, negative 1 to the power of n times an converges provided it satisfies these two conditions. An plus 1 must be less than or equal to an. That means the terms of the series must decrease in magnitude. And the limit as n goes to infinity of the nth term an must be equal to 0. If the alternating series satisfies these two conditions, we say the alternating series converges. All right, and it has, of course, a finite sum. So there's a caution. For positive term series, summation an, the limit as n goes to infinity of an equal to 0 does not imply convergence. But for alternating series, summation n equals 1 to infinity minus 1 to the n plus 1 times an, with decreasing terms, the limit as n goes to infinity of an equal to 0 does imply convergence. Let's look at example of this. If you look at summation n equals 1 to infinity 1 over n, this is a divergent p-series. But notice that the limit as n goes to infinity of 1 over n is equal to 0, but still it diverges. Now, if we tweak it a little bit and put an alternating sign in front of it, negative 1 to the power of n plus 1, this is actually going to be convergent by the alternating series test, and we're going to prove that. So we have summation n equals 1 to infinity minus 1 to the n plus 1 times 1 over n. And we want to prove that this series converges by the alternating series test. Let's look at the two conditions. An plus 1 less than an. That means every term is less than the previous term. So let's test that. An plus 1, that's 1 over n plus 1, is less than 1 over n. Well, that's true because 1 over n plus 1, we're increasing the denominator. That means the ratio becomes smaller. So that means the terms decrease in magnitude. decrease in magnitude. Now, let's check the second condition. The limit of the nth term should be equal to 0. Limit n goes to infinity of an is equal to 0. Let's check that. So we have the limit as n goes to infinity, an is equal to 1 over n, and clearly this limit is 0 because we have 1 divided by a large number. So both conditions are satisfied, both conditions of the altering series test. So we say that summation n equals 1 to infinity minus 1 to the power of n plus 1 times 1 over n is convergent by the alternating series test. Convergent, we're going to abbreviate this. It will be much easier to write by the AST, alternating series test. All right, let's look at a little bit more of a difficult example. Here we have tested series summation n equals 1 to infinity, negative 1 to the power of n times n divided by n squared plus 1 for convergence or divergence. We have to check the two conditions. So number one, decreasing terms, an plus 1 is less than an. Well, it's not clear that the terms given by an is equal to n divided by n squared plus 1 are decreasing. So we're going to apply the derivative to prove that. Let's consider the related function f of x is equal to x divided by x squared plus 1. Let's take the derivative by applying the quotient rule. So f prime of x is equal to square the bottom, x squared plus 1, all squared, take the bottom, x squared plus 1, times the derivative of top, derivative of x is 1, minus the top times the derivative of bottom, which is 2x. If we simplify this, we're going to get 1 minus x squared divided by 1 plus x squared, all squared. Now, we know that f prime of x is less than 0, the derivative is negative, f prime of x is less than 0, when the numerator is negative, because the denominator 1 plus x squared all squared is always positive. So 1 minus x squared less than 0, that means x squared larger than 1, which of course means either x bigger than 1 or x less than negative 1, but we're only considering positive term series. So let's take x larger than 1, and that means f of x is decreasing on 1 to infinity. That means the terms are decreasing. An plus 1 is less than an for n larger than 1. Now, when we say an plus 1, specifically we mean n plus 1 divided by n plus 1 squared plus 1 is less than n divided by n squared plus 1. And we use the derivative to prove that. So now let's check the second condition. For the second condition, the limit as n approaches infinity of an has to be equal to 0. So let's take the limit of the nth term. Limit n approaches infinity of n divided by n squared plus 1. So divide by the highest power in the denominator, divide by n squared, divide by n squared, divide by n squared, and we get 1 over n, 1 plus 1 over n squared. Take the lim as n goes to infinity, 1 over n, this is going to go to 0, 1 over n squared goes to 0. The result is 0 over 1 is equal to 0. So we say the given series, summation, n equals 1 to infinity, minus 1 to the n plus 1, times n divided by n squared plus 1, is convergent. This series converges, the series is convergent by the alternating series test, and we will abbreviate AST. So it's always important to check both conditions. If both conditions of the AST are satisfied, then the given series is convergent by the alternating series test. All right, thanks.